You ever got a song stuck in your head and you don't know what it is? You hum it into your phone, and within half a second, it gives you the song's name? How does that even work? And what if you're just bad at humming and it's loud and you're in a restaurant? Well, the secret is, just like how text can be converted into binary for a computer, so too can sound. It's just, you can't see it. This idea that sound can be changed into a form a computer understands is key to digital sound processing. Just like pictures or words, sound can be broken down into simple parts, which lets computers work with it easily. Sound travels through the air as waves that rise and fall. Our ears pick up these waves and convert them into signals our brains understand. Phones do something similar using a microphone. The microphone senses sound waves and turns them into digital data, numbers stored in the phone's memory. Once music is captured as data, an app can analyze it. This analysis includes looking at how loud or soft each note is and how these notes change over time. By studying these variations, Shazam can form a unique picture of the audio it hears. To capture sound, the phone takes many quick measurements of the audio. Each measurement shows how strong the sound is at that moment. These numbers enable the app to study the sound in detail. But Shazam doesn't need to listen to an entire song. It only needs a short snippet, usually a few seconds, to gather enough information. During this brief window, the app records the sound and prepares it for deeper study, even in noisy environments. That short snippet holds plenty of clues about which song is playing. Under the hood, Shazam uses advanced math to create spectrograms, a heat map of sound over time, where one axis shows time and the other shows frequency, or indicating how high or low a note is. A key tool in this process is the fast Fourier transform, or FFT, which splits sound into different frequencies and breaks the music into smaller parts that are easier to compare, much like how text is decomposed into strings of ones and zeros. Although this might sound intimidating, the core idea is straightforward. The FFT identifies which notes are present and how strong they are at each moment. Shazam then flags the strongest notes, commonly referred to as peaks, and discards the rest, significantly reducing data storage needs and expediting the matching process. Using the FFT is a major breakthrough in analyzing sound. By turning time-based data into frequency-based data, the FFT provides a clear view of the basic tones and harmonics that form a song. This transformation makes it easier to pick out key parts while also reducing the amount of data to process. Spotting peaks is very much like discovering the most crucial markers that define the song's structure. In a song, certain sounds, such as a loud drum beat, a clear vocal note, or a sharp guitar chord, stand out more than others. Shazam focuses on these standout moments by pinpointing peaks with specific frequencies and appearance times. By concentrating on these peaks instead of cataloging every note, Shazam reduces the data it must handle while ensuring a smooth, near-instant user experience with the heavy lifting done behind the scenes. Speaking of, thanks so much for all the support on the channel lately. It really means a lot, and I want to give something back to you guys. So do you need a job? That sounded a bit weird. But whether you're a UX designer, app developer, freelancer, or just a curious viewer, I want to get to know you guys, share some UX and UI tips, and maybe even get a gig. So I made a Discord channel for us and want to make this the place to be for front-end professionals. And I'm having talks with people to get some employers in there so you can connect with them too and find some jobs in the future. I'm really excited to get this thing started, so I hope you'll join me. Once Shazam finds these peaks, it groups them to form a distinctive fingerprint for the audio clip. Think of a fingerprint as a set of special markers that no other track shares in exactly the same way, much like an actual fingerprint. Each marker shows a peak's frequency and the time it occurred. When you combine all these markers, you get a pattern unique to that snippet of music. Then comes the search. Shazam uses a method called hashing, which transforms the information about each peak into a shorter bit of code. For instance, it might combine the frequency and time into a single number or a compact string of digits. This step is vital because searching through millions of short codes is faster than comparing entire blocks of raw audio. Each snippet from your phone is turned into multiple hashed codes, which Shazam then checks against its huge library. When it spots a match, it knows it has likely found the correct tune. Hashing works like a shortcut that lets the system skip lengthy comparisons of massive data strings. By turning complex details into simple codes, the search becomes much faster. This speed is crucial for ensuring users receive quick responses, reinforcing the smooth experience that has made Shazam a well-known, reliable, and trusted application. Shazam's song library is enormous, covering everything from pop hits to obscure tracks. Each song in that library has been pre-processed. The entire track is broken into segments, and each segment is turned into its own fingerprint. When your snippet arrives, Shazam doesn't compare it to the entire song at once. Instead, it checks your snippet's fingerprint against every segment's fingerprint. If it finds enough matching peaks, it declares a match. This approach is both fast and precise, allowing the app to recognize a song even if your snippet starts in the middle or near the end. One of Shazam's greatest strengths is its ability to work in less than ideal conditions. Maybe you're in a crowded bar with people talking, glasses clinking, and music echoing from different speakers. Shazam's focus on peaks makes it more resistant to random noise. Soft sounds and background chatter rarely affect those key peaks. Even if there's some distortion, the overall pattern of loud, distinct notes remains recognizable, which helps the app pinpoint the right song. As a result, you can often Shazam a track even in places where the music isn't crystal clear. And sometimes you might hum the music out of tempo, but it doesn't matter. Shazam still has a good chance of finding the match because the relative spacing between peaks often remains the same. Even if everything is shifted by a small fraction of a second, the app can align those peaks in its database with the peaks in your snippet. This flexibility ensures Shazam can work for anyone, not just musicians. But obviously, it's not perfect. There are times when it fails to identify a song, especially if that track isn't in its database or if the recording is very poor. Rare or unreleased tracks might never show up because Shazam relies on pre-stored fingerprints. Still, the majority of popular and even semi-popular songs are listed. The app also updates its library regularly, improving its coverage. Most users find that Shazam gets it right a high percentage of the time, and its speed is one of its biggest selling points. And it's gotten so good that it's starting to inspire other fields. Similar techniques can detect specific bird calls in the wild or pick out whale songs in the ocean. Doctors use related methods to analyze heart sounds, looking for patterns in a heartbeat that might indicate a health issue. The idea of turning complex audio signals into identifiable patterns has many possible uses. Shazam shows just how effective this approach can be when done on a massive scale. So next time you tap Shazam to learn the name of a catchy tune, remember, there is a neat mix of sound science and smart data work hidden behind that simple button, just like how there's visual science behind the world's biggest map app.